Hello and welcome back to another video and also to my messy desk because I've been busy. So in the last video I showed you guys my Arduino based controller where I took the Xbox One controller and interfaced it with an Arduino to create more or less of a universal controller for my bots, and I said that it was sort of stretching the limits of what I can do with an Arduino Uno. So here we are today with a controller that runs on full-blown Linux on a Dragon Boat 410C, and yeah, just wanted to show you how it all looks and how it all performs. So here's a little sneak peek. This is what it looks at the front. All the parties on the back, it's all business on the front. um, I'll show you the hardware. We'll take a look at it running, and then we'll take a look at the code. So this is the Xbox 360 controller. It's mounted to a phone holder thingy, and on which the screen is attached on the clamp and everything. All the electronics is basically double-sided taped to the back of it, and the screen is a 5-inch display. We'll go more into the details about the screen now and how it's all interfaced. Now at the party side, I've tried to make it as clean as possible, and this is how it looks like. um, so we'll start, we'll peel it layer by layer. That's the screen. This is an Adafruit unit. So this is a 40-pin LCD display in place of a 50-pin one. I only had 7-inch displays for 50-pin ones. This is a 40-pin one. This is a Adafruit interface for 40-pin TTL RGB displays. You can see the fat flex from the display here to an HDMI port, and these are flat flex HDMI cables. You can get it at multiple places. There's not really a brand, but Adafruit sells them, I think, in India. Crazy Pie and Thingbits sells them. A couple more folks. So it goes from to the Dragon Board's HDMI port right there. Talking about the Dragon Board, it's sandwiched right here. The reason I'm not peeling anything off is it's all double taped. I'm not going to reassemble everything, so deal with it. Here's a Dragon Board. The reason I use a Dragon Board, it's just more reliable. I've had issues with a Raspberry Pi. The power consumption is too much. Sometimes the power ICs just give up. So I had an extra Dragon board laying around. The problem with this one was all of the GPIO pins were sort of damaged and ripped apart because of corrosion. This was sitting outside for a long time. And if you've never seen a Dragon board before, this is what a Dragon board looks like. It's a Qualcomm. It's powered by a Qualcomm 14C processor, so a quad core Cortex A53, and we'll also get to the point why we need a quad core Cortex A53 for remote control. Kind of overkill, but not really. We'll get into that later. And that's about it. It has onboard eMMC, so I'm not using an SD card, so again more reliable than a Pi in that manner as well. Powering it all is a 1000 mAh 3.7 volt battery, and that Lipo pack, single 1S Lipo pack, um, lasts for an hour, so the power draw from it is just around an amp. This is a Lipo Charger, and booster, so voltage booster. The Dragon board runs at around 8 to 18 volts. It has a wide voltage range. 5 volt is not in that voltage range, and running it at 5 volt or even close to 6.4 volts for a 2S Lipo pack when it's kind of discharged can cause brownouts, and I do want to not cause brownouts. So we are boosting the voltage to around 9 volts, I think. There's little potentiometer somewhere there. It is teeny tiny thing, and that allows us to boost the voltage. And it's actually really efficient. So I calculated around 95% efficiency on the conversion. So that was all good. So that's how we charge it. My power button is a bit on the side. I could have had a much better one, or at least tucked it down, but we'll see what to do with it later on. Um, So I'll explain the USB ports in a second. But over here, I recently discovered these things. These are battery power meters, and you can set them for 1S, 2S, up to 8S cells. And you can just switch them on and they just tell you the current charge percentage. So 100, 75, 50, 25, and when it's only the red stuff lighting around it, that means it's sort of really low and you better charge. So right now it just shows 2 points. I don't know if that's, yeah, that might be a bit better. That just shows 2 points, so it's around 50% charged. We'll power that off. The way that's connected to it is this LiPo has two separate leads. So they were trying to do the balance charge thing. So they had one charge lead and one power lead, something like that. And they are basically just connected to each other. There's nothing separating them. So I just connected the other leads from the same LiPo pack to that. Right. So I wanted to make it clean. I wanted to make it look clean. So instead of having the USB ports poke too much from the top, and my EDA friends will hate me for this, but I have just broken out USB 2 in a messy sort of nest of wires, and we have two USB 2 ports here, so they're just pass throughs. So that sort of tucks the cable for the Xbox controller, as well as the TTL to USB for our transmitter. Now this is the same one I've used on the Arduino project, and I'm trying to figure out the best case scenario, but HC12s are just super simple to use. Maybe one day I'll try to move to something more like this, but till then, HC12 will have to do. All right, time to power it on and see how it works. Let's see, I think I'll need to switch off the lights in order for it to show properly. Right, I'll turn that off and we'll turn this on. So it takes 5-6 seconds to boot, but the actual issue is that everything needs to start up, and then so I should make a proper systemd service for it to start the app itself, but it's right now just a bash script that sleeps it for like 10 seconds after boot and then starts it. So yeah, maybe later. Right, so the way this works is this is entirely written on LVGL, so that's light. I forgot the full form, but it's a lightweight graphics library, and yeah, light and versatile graphics library. I think that's the full form. So you can basically run this UI on an MCU. You just copy the code, make sure your display stuff set up correctly, and you can run this on an MCU. So LVGL runs from any 32-bit MCU to your 64-bit Linux systems. This draws directly to FBDev, so you don't have to go through any weird hacks to get the graphics set up or anything. You can just boot even if you don't have a GPU. If your SOC just has a simple display out, that can still work. So the top two rows of icons are just response to whatever buttons I push on the controller. So as you can see, as I'm manipulating the controller, the things highlight. I just looked fancy and looked nice, so I added that. So D-pads right here, and all my X, Y, B buttons are here, my shoulder buttons are here, my analog throttles are here, and here are the sticks, the Xbox button, and we'll talk about the menu button in a bit, and the simple stuff. So the 4 meters you see here are basically response from the ECU, and I'll show the ECU in a second. from the bot, from the rover, about the amount of PWM that's going to each wheel. So say if I give around 50% of throttle, that's how much the PWM there is, and if my fingers are unstable enough, that will fluctuate. And if I move the stick to the left, um, the PWM on the left side of the wheels decreases since it's like differential steering. This will move the rover in the left direction, and same if I move it to the right side changes. So we'll do a bit more sort of complex math later when we add RPMs and all that stuff, have it react to the RPM, etc., etc. So that's the situation right now. The left throttle is going backwards, the right throttle is going forwards. The PWM value stays the same whether it's going forward or right. It's a simple bit flip on the direction pin, and that's why the meters just show the same whether you're going forward or backwards. So those meters are direct response from the ECU. This is what the ECU looks like. I should probably open up the lights a bit and sort of show it to you properly. Um, the entire rover project is sort of in a position where I don't know whether it's ready to show off or not. But this is just the ECU bit. The 40 pin connector you see on your left is where everything connects to the main powertrain, as I'm calling it. So you'll see what that is maybe in later videos this week or the next. Hopefully I can get a couple more things working, just enough to make it worth your while to watch. And yeah, so same HC12 here and HC12 on this one. And I can basically it just data coming in from the ECU depending upon how much throttle I send in. So that's the software till the point. There's a lot of stuff, there's a lot of area remaining where we'll have other metrics from the ECU displayed, and maybe even have multiple pages, and just use the D-pad to switch between the pages and have more info or different driving modes or things like that. I think the battery just ran out, which is rather happening rather quickly these days. It lasts for about an hour. I've been recording for a while, so I'm not surprised that it ran out. That is sort of one of the things I wish I had thought about. Controlling or figuring out is auto shutdown. But my GPIOs are all sort of unusable at the moment on the board, and I don't really want to open and get on it. So I'm going to live with it for the while, for the time being, unless I can figure a simple like MOSFET based solution or something where it can send a shutdown command easily. Um, so yeah, that's the controller, and we'll now go and take a look at the actual code. Alright, so here we are at the code. As I said, it's basically LVGL UI all the way through. So I'm not going to explain the entirety of the code. You can see it on my repos. I'll link it down below. It's around 786 lines. Alright, so the reason I really needed a um, a multi-core CPU, if not, so I tried this entire code with the Pi 0, and what was happening is the way I'm handling everything is with P threads. So the main thread basically runs LVGL. So that's your main, and it sets stuff up for the other threads, starts the other threads, and basically starts all your LVGL stuff, starts the FBDev driver for the LVGL, and then just this entire the LVGL thing is simple to use, simple to code. It's just a lot of code that you manually have to put in. So a lot of cut, copy, paste code. So you can see these blocks are basically identical with like minimal changes to the object name and the pixel the position and the size, So the sizes here are different, the position on the display is different, and all of that stuff, minor changes here and there. Basically this entire block is a big cut copy paste stuff. And then here's the main while loop where everything reacts to everything else, and the data is coming from a struct called stick. um, Struct called joy, and strict is the object I created for that struct. There you go, strict stick. And yeah, you have to sort of initialize the struct, otherwise it gives weird values at the beginning. Take care of that. So the fun part is, so that's all the input from the joystick, right? The send thread and receive thread, there was a function called receive thread, but I sort of mixed it in the send thread as well, because I see the way Linux handles raw UART comms from the user space side in a very complex manner. No MCU does it like that. No RTOS does it like that. If you look at code from Arduino, if you look at code from Zephyr, it's so much simple. But for some reason at Linux, you have to set all of this crap up, like all of this. Why? Where are the defaults? Like, why can't just say here's the TTY speed at like 1520008 and that's it? But no, all of that has to be said, taken care of. And then you have to go into here and you have to, there's only like read buffer, send buffer. Send, I think, can do multiple buffers, or read you have to do like one at a time. There's some complexity here. You can't do read until, which is a really good way, in a way a lot of UART communication, raw UART communication happens, where you read until a stop character. Maybe it's backslash r, maybe it's 0xff, maybe it's anything else. And it just reads till that character and stops and saves all of that to a buffer. And that's how I handle it on Zephyr for the most part. I don't think it's directly read until buffer, but it's pretty close. Um, but you can read a specific size. You can read, like, just continue reading to a buffer till the UART stops for some time. So like, all right. So the reason you don't need e- all right. So the reason you need a multi-core CPU to run this is because of the main thread always continuously being busy on on updating the LVGL stuff. Even if you have some basic, you have a 5,000 microsecond sleep there. But even if you do have that, the Pi Zero couldn't context switch fast enough to read the joystick values. And what would happen if I leave the trigger, like if I flick the trigger, it would not flick from completely pressed to completely depressed. It would stay somewhere in between, because it would miss those calls because it's busy updating the LVGL screen. And if you just have another CPU to handle all of that, or two more CPU, one to handle your main, one to handle the the thread that does the joystick stuff, another one to handle anything in the background, the kernel, I guess. It basically sort of smooths things out and makes sure that the system's responsive. Or if you just have one single CPU, make sure it's actually really fast. Like maybe a BeagleBone can work. I don't know. Maybe it will. But as far as this project is concerned, Dragon Board is working fine. The CPU usage is around 25% on one core, 10 to 20% on another. seems fine enough. Yeah, so that's why you need more than two cores. It's just because the two main threads that take the most time um, are really requiring a fair bit of resources, and not just a fair bit of resources, but they update so frequently that context switching actually costs you performance and costs you time. Like, it's not a real time OS, so like Linux will fail to sort of, um, it will miss some calls because it's basically an interrupt based thing for the joystick. The joystick sends an interrupt saying that, hey, I have an update to the throttle response value, like the throttle value, and if the CPU is busy for extended amount of time on, say, updating the display, it will not get that interrupt, it will not talk to that interrupt. Whereas in an RTOS, it usually leaves the stuff it's doing right now, and if it's a high priority interrupt, it goes and talks to that. I could have done um, the RT patch stuff on this, but eh, on the Pi Zero. But it just sort of makes my life easier knowing that I have a bit more room to play with. So just to prevent all of that, interrupt misses with CPU being busy, context switching between, say, LVGL um, and your joystick events, it's usually better to just have a faster board or like something with multiple cores. I'm pretty sure something with like A7 dual core will work just as fine. Again, Dragon board was low power and was just something that I had laying around. So yeah, that's about it. That's my rant on why Pi Zero might not be a good fit for everything, and why why I hate programming UART stuff on Linux user space. I mean, I've not tried programming it on any other OS's user space apart from RTOS's, but maybe this is how it's on any non-RTOS OS. Who knows? Uh, yeah, thank you so much for watching. I hope you all enjoyed this, and I'll see you all in the next one.